Okay, good morning, everyone. So I thought today I would do something that I don't usually do, and that's go over a couple of homework problem issues that we had on homework set 4, which I've emailed back to you. But the reason is mainly because, well, the first one I want to talk about is homework for problem 1. And the thing that happened there is most of you got the hard part of the problem, but then the important conceptual part that was supposed to be easier caused a lot of confusion. So let me remind you that in this problem, we were given the 3D harmonic oscillator that's isotropic. And so the potential is just this thing, quadratic in the coordinate r. And so before doing it, let's remind ourselves of what the exact answer is supposed to be. So that you can go from looking back in the notes from last semester. And so the energy levels are h bar omega times 3/2 plus k plus L. And this is equation 8.5.25 in the notes. And the interpretation of these is L is the angular momentum quantum number. And then k is something that has to do with the radial wave function. So this is a radial quantum number. And these are both integers. And so if you want, you can rewrite this in terms of a single integer, which it's traditional to call n. Okay, so n is also an integer, but here's the key thing that I think caused a lot of confusion. N here, oh, by the way, this is equation, where is this in the notes? This is equation 6.5.13. But it's just rewriting the previous equation. This is an integer. But the key thing is that n has nothing at all to do with the n in the problem. So this has nothing to do with our n. Because our n in the problem had to do with a trial wave function. And the trial wave function that we picked, or that I picked for you, was radial coordinate to some power, which I decided to call n, e to the minus kr, and then something that has the angular momentum information in it, namely the spherical harmonics. And so that spherical harmonic is just there to affect the effective potential. Okay, and so from the kinetic term, or I guess I called it mu, that gives you an L times L plus 1 dependence. Okay, but this n in the trial wave function is just a completely conceptually different thing from the n that appeared in this other equation. And because there are only 26 letters in the alphabet, we just have to get used to the fact that sometimes the same letter stands for different things. In fact, we do this all the time. For example, this e in the exponential here, we don't mention it often, but we're using E also for the electric charge. And it's just something we have to get used to, that whenever we see a variable, we have to make sure we conceptually understand what it stands for. So in our case, n and k were the variational parameters. They're something that we are supposed to adjust in such a way as to minimize the energy function. They are part of our guess and not really part of the actual true state. Okay, so when you did this, you should have found, and I think most of you did find, that it went like 1 part over k squared plus another part times k squared. And so one good problem solving strategy is that when you have something like that and you're minimizing with respect to one of the variables, you can temporarily just give these things names A and B. These are things that depend in some complicated way on N and L, but when you're doing the calculation, you don't want to keep rewriting that complicated dependence. So when you minimize with respect to K, you get some K minimum. And in terms of A and B, it's really easy. It's just B over A to the 1/4.
Professor?
Yes?
What's that on the denominator of that Laplacian negative h bar? Is that mu?
Oh, here? Yeah, this is mu.
Okay.
Okay. And so K min is just a simple thing in terms of B and A, and so is the minimum E. So it's just, right? If we're minimizing with respect to K, it's just 2 times the square root of AB. Okay, and then having found that, you can go ahead and plug in the complicated A and B. And here's where, again, it's useful to simplify things. Okay, and so you should have found, let me just rewrite this. It turns out to be h bar omega times some square root of some fairly complicated thing plus n plus 1. The point I'm making here is that it's better to eliminate all the factorial stuff, which is not hard to do. And so there's no actual factorials in this. Okay, and then the strategy was for parts C, D, and E, which I'd intended to be the easy part. You're just fixing L and you're varying N. Okay, and I've asked you to decide which N is the best N. So the key point here is the best N is always the N that minimizes it when you're doing the variational principle. So best variational parameter is always the one that minimizes the energy. So many of you tried to match this N that here in this formula with this N that you knew was the correct N for the exact answer. But the problem is they're completely different N's. They have nothing whatsoever to do with each other. Okay, so anyway, I just wanted to, one more comment I wanted to make is this trial wave function that I gave you is really given to you mostly because it's something that's relatively easy to compute with without being the exact answer. The only thing I could have given you that would have been easier to compute with would have been the actual wave function itself, and then you would have minimized it and you would have found the exact answer, but that's too easy. So I gave you this instead, which is admittedly harder. The key thing about this wave function is it's really a bad approximation to the wave function. Because, for example, in the ground state, the true ground state is a Gaussian. And here we're trying to approximate it with something that grows with R, which a Gaussian does not for small r, multiplied by an exponential. At least that's falling for small r. But this is really bad because this doesn't look anything like a Gaussian. And yet, let's see how well it did. So if you plugged in the N that actually did the best for each L, okay, so for L equals 0, that was part C. So you're just taking this expression, plugging in L equals 0, which kills that, and then just tabulating for different N's what you get by computing this. Okay, and so the answer, so first of all, the exact answer is not something that depends on n, because n is going to be fixed. The exact answer is 3/2 h bar omega. And the one that gives the n that gives the smallest value turns out to be n equals 1, which turns out to give an energy of 1.58 h bar omega. So even though it was a terrible attempt at a trial wave function, this is the key lesson of the variational principle, is even bad guesses give you good answers for the energy, because 1.58 is not that far from 1.5. And in fact, it gets better as you go to higher angular momentum. And again, the reason we can treat different angular momenta differently is because the angular momentum commutes with the Hamiltonian. And so we can do the variational principle separately for each different value of L. Now, we can't do the variational principle for each different value if we look back up here for K, because there's no corresponding operator that commutes with the Hamiltonian that we can say, oh, those two things have common eigenstates, and within each common set of commuting observables, we can do the variational principle separately. Okay, so getting back to here, for L equals 1, that was part D. And so what you're supposed to do is just plug in L equals 1 here, then take the rest of it, just write down all the different answers for different n, figure out which one's the lowest. And so here, the exact answer is 2.5 h bar omega. And it turns out the n that minimizes the variational principle was n equals 3, which turns out to give E equals 2.54 h bar omega. So again, much better, much closer than we had any reason to expect. And then for L equals 2, which is part E, the exact, again, these do not depend on n because n is fixed to be the minimum, which turns out to be n equals 5. And the energy was, in this case, 3.52 h bar omega. So already for it works better for larger L. Sorry, this is L equals 2. For larger L, this thing gets better and better. And you can sort of see that by staring at this thing under the square root. Because what's happening is when L gets very large, then we just have something that goes proportional to L. And then some stuff here that for larger n is just approaching 1/2. So this thing just automatically knows that it's supposed to go to the right value for larger L. So again, these are the exact, and these are the variational things that you get by minimizing with respect to our n. Okay, so lessons of this that you should keep in mind. Same letter, stands for different things. Very important to make sure you know conceptually what something stands for before applying it. And the other key thing is variational method, just the very structure of the way it's set up, the lowest is always the best by definition. Okay, and then I guess the third thing is it works better than you have a right to expect, given that you might put in a bad wave function, but it still works pretty well. Okay, enough about that. The other problem I wanted to comment on was problem 2, because there was actually a lot of people didn't get this either, and there was supposed to be a lesson to be learned from this. So here I remind you, the idea was to get the Darwin term, which wasn't too bad, especially since you already knew the answer. We already said what it was. So the change in energy from the Darwin term, and we did it first for hydrogen, which means Z equals 1. And you should have gotten fine structure constant over n cubed times a Rydberg. Okay, but then I threw a curveball at you and said, okay, how does this scale with Z for larger atoms? So how do we think about this? Recall the setup for what a problem with a larger Z looks like. You've got a nucleus with charge Ze, and you've got an electron with charge minus E. And the Hamiltonian, they're attracting each other. The Hamiltonian is a kinetic term, which certainly doesn't depend on Z. And then a potential term, which has this dependence on Z. So the moral of the story here is that if you are writing your problem in terms of the input parameters, which in this case, if you look at it, there's only two inputs. There's the mass of the electron, and there's the charge on the electron, along with Z, the other parameter. And so the moral of the story is written in terms of the inputs of the problem. So inputs, electron charge and electron mass, then you can replace E squared in the hydrogen atom with Ze squared for a general. And you don't do anything to the mass of the electron because the mass of the electron is what it is. So really the moral of the story is that any quantity that you derive from this general setup, you get from this replacement. You always take E squared and replace it by Ze squared. So let's see what that means for different quantities that we can write down. So for example, there's the fine structure constant, alpha. So if you look up what alpha is, it's E squared over H bar C. H bar C are constants of nature. So this is going to be replaced in our problem by Z times E squared. And so it will be replaced by, it will turn into Z alpha when we go from the hydrogen atom to a general atom. There's still one fine structure constant. The fine structure constant is always defined to be alpha, but this is telling us how in this problem, what do we replace alpha by? We replace it by Z times alpha. Okay, and then there's the Bohr radius, for example. The Bohr radius is, if you look back at its definition, H bar squared over E squared, M sub E. And so that gets replaced by, when you're going to some other atom, the Bohr radius divided by Z. So just qualitatively to understand why that is, if your nucleus has more charge, then it's going to be more attractive to the electron. It's going to pull the electron in closer. And so the larger Z is, the smaller the effective radius of the ground state will be. Okay, so that makes sense. And so now we can do this for our Darwin energy. So if I write the change in the energy from the Darwin term for a general Z now, we just go back up to this expression and we just say, okay, alpha gets replaced by Z alpha. And there's two of them. And E squared gets replaced by Z E squared. And the Bohr radius gets replaced by the Bohr radius over Z. And then we can keep track of the n cubed. Okay, and so if we count up all the Z's, this is proportional to Z to the fourth. Okay, now that's in contrast to the main energy term, which remember for hydrogen was Rydberg over 1 over n squared. And so this for a more general atom will be Z squared E squared over 2 times the Bohr radius times 1 over n squared. And there's actually an equation to that effect somewhere in the notes, because actually when we derived this last semester, we did it for a general Z. Okay, so the unperturbed energies go like Z squared over n squared, and the Darwin corrections go like Z to the 4th over n cubed. And so what we were supposed to learn from this problem is that the fine structure, of which the Darwin is one part, but the rest of the fine structure actually obeys the same scaling, is more important relatively it also is coming from relativity for larger atoms. And it's more important by a factor that goes like Z squared. So if you're talking Z is 20 or 30 or 50, this is saying the fine structure is less and less ignorable. You have to be more careful to include it if you really want the right answer. But it's also less important for excited states, relatively. And that's because it's got an extra power of n in the denominator. All right, so that was all I wanted to say about those two homework problems. We're going to come back to talk about atoms a little bit later. And so it's important to know this principle that the fine structure becomes more important when you're talking about larger atoms than hydrogen. Any questions on that? All right, so now let's get back to what we were talking about with identical particles. And so we were going to return to the helium atom that we've studied twice before. The main difference with today is today we're going to not just talk about the helium atom ground state, we're going to talk about the helium atom excited states. So let's draw our cartoon of the helium atom. Here's our nucleus. I'm still going to call this Z. And then we have an electron here, and we have an electron here, and they're identical. So I can call this coordinate R1 and this coordinate R2. And then our Hamiltonian is a kinetic term for each one of them. And then there's an attraction of the electron that we've decided to label R1 to the nucleus. And the same thing for R2. And then there's E squared over the difference between them, because they're going to repel with 1 over that distance. Okay, and so one of the reasons we're writing this for general Z is just to emphasize the point that when we go to larger and larger atoms, it becomes not so bad approximation to ignore, as a first approximation, to ignore that compared to the bigger contributions from here. Okay, and so for helium though, we can go ahead and plug in Z equals 2. And then when we did the ground state, remember our strategy was to make a first guess to, and that was just to ignore the last term. Of course, you have to put it back in later. But if you ignore the last term, then your guess for the total state of the system, written as a wave function, is it depends on R1 and R2 and the spins. And since we're ignoring the cross term, we can just treat the two parts of the Hamiltonian separately. And our ground state looks something like this. It's the product of two individual ground states times a spin state. So a reminder, this is the spin 0 state. This is anti-symmetric. under interchange of the spins. And more specifically, it's this combination. Okay, we take the difference between up, down, and down, up with the 1/√2 for normalization. That's anti-symmetric, which leaves this part free to be symmetric because we're talking about identical fermions. And we've built it as our first guess out of hydrogen-like ion states. So each electron in this just ignored the other electron to start with. And then what we did is we applied the last term using two different methods. One was first order perturbation theory. That one did not so bad, was a few percent off from the right answer. And then we did the variational method, which did even better because the variational method often does a little bit better. And we did this to include the last term. And if we wanted to, we could have done second order in perturbation theory, or we could have done a more complicated variational method, trial wave function, and we could have pretty much done as well as we wanted. The point being here that when we did this, I just completely didn't write this down. But the reason we could get away with that, and it gives the right answer anyway, is because this is a singlet state. There's only one spin zero state anyway. And so whatever it is, it just multiplies the whole rest of the state. And you don't have to worry about, for example, mixing between different parts of it, where you'd have to do degenerate perturbation theory, because there's only one of them anyway. Okay, so all of that was for the ground state here. And now let's talk about what about the excited states. Okay, so again, our first guess is going to be just ignore that last term. So first, ignore e squared over r1 minus r2 again. And again, use hydrogen-like wave functions. The only thing we have to be careful of course, is that when we use hydrogen-like wave functions, we're doing them with z equals 2, not z equals 1. That is, if we're doing perturbation theory. And we're again going to assume that one of the electrons is in the 1s level. We will come back to why that's a good assumption in a little bit. So 1s just means principal quantum number 1. S means angular momentum 0. But now we're going to take the other one to be in whatever level it wants to be in. Okay, so our wave function is going to look like this. I'm not writing the spin part. I'm just writing the wave function, the spatial wave function part. So it's going to be 1/√2. Here's my electron that's in the 1s ground state level. And then the other one's in some other level, which I don't want to be the ground state because that would just give me the total ground state. So now having written that down, I know I have to put in the same thing with R1 and R2 interchanged, and that can be either plus or minus. So I'm going to write psi1, 0, 0, but now as a function of R2, and psi n Lm, but now as a function of R1. Okay, and if I choose the plus sign, then it's symmetric. Then that wave function is symmetric. And so then I must have the spin state be antisymmetric, just like for the ground state. So I have no choice about that. the spin part has to be spin equals 0 because that's anti-symmetric. Okay, but the difference is that now I can choose the minus sign. Okay, for the ground state, I couldn't do that because if NLM and 100 are the same, then I'll just get something minus itself and I'll get 0 and that's the null ket, so it's not a state. But for NLM, anything different than 100, I can do this with the minus sign. Then it will be anti-symmetric for the spatial part of the wave function. And so then I would need my spin part to be symmetric, which means spin 1. So that's symmetric. Symmetric and anti-symmetric always mean with respect to interchange of the labels. Okay, so the plus sign is called, as jargon, perihelium. Okay, and the ground state, therefore, is an example of a perihelium. So was ground state. So when you hear perihelium, that just means the spin was spin 0. And if we chose the minus sign, that's called orthohelium. Okay, and the ground state could not be orthohelium, is one thing we learned from that. Okay, now let's suppose we're going to do perturbation theory on this. Or let's say we're going to do the variational principle, but we're just interested in the part of the variational principle energy that comes from the first part of the Hamiltonian, the part we didn't ignore yet. So in both cases, the unperturbed energy is just the sum of the energy of the 100 plus the NLM. Okay, and so we can write that down as minus z squared, which is secretly 4. Okay, and then there's a 1 for the 100, and there's a 1 over n squared for the NLM. And of course, we're ignoring the fine and hyperfine for now, which we will come back to in a little bit. Okay, so that's our unperturbed energy. And now we need to include the perturbation, or the last term that we've been neglecting. Okay, and so I'm going to phrase this as if it's perturbation theory, but the same thing would apply if we did variational. That's our perturbation Hamiltonian. So I'm going to be including this as a perturbation. And so we know what to do at first order in perturbation theory. We calculate the change in energy as the expectation value of the perturbation Hamiltonian. I'm assuming this is normalized, so I won't put in any denominator. And so the point is that when you calculate this, it's really got two terms to it. And I'm going to write them as I and j. And they differ by the same plus or minus sign that came in here. Because when I calculate it, what's going to happen is I'm going to get some integrals to do, and the integral will come out one way if it's positive and the other way if it's negative. Okay, so it's got that general form. And so the general form is you use the plus sign for perihelium, which means spin 0, and you use the minus sign for orthohelium, which means s equals 1. Okay, now let's go ahead and write down what I and j are. I is otherwise known as, well, let me write it what it is first. So when I evaluate that expectation value, I'm going to have an integral over both R1 and R2. And then I get my wave function for the 100 state. And then I get my wave function for the NLM state. And then I write down my Hamiltonian part. And so we did a similar integral for the ground state, but now it's complicated, more complicated because we have NLM here. And it's sufficiently complicated that we're not going to do the integral. This is known as the direct integral, though. That's the terminology for it. So it turns out there's another contribution that you get by writing R2 here and R1 here, but really they're the same thing, because then I just relabel my integration variables, and this thing doesn't care whether I write R1 minus R2 or R2 minus R1. So it actually contributes the same amount. Okay, and so one key thing about this integral, even if we don't compute it, is that it's positive. So how do we know it's positive? It's positive because we're integrating over a bunch of things that are themselves positive. This is the complex square of something, that's positive. This is positive, and this is positive. So the whole thing is positive. Okay, and then if you calculate the rest of it, the J part, it looks very similar. The difference is the J part is going to come about when I come back to my wave function up here. When I take the whole square of this, what I've basically included is this squared and that squared, but now there are going to be cross terms between this and that. So that's what I'm going to write down here. And so the answer is psi 100 R1, psi NLM R2, and then psi 100 complex conjugate, which actually doesn't do anything here because it's a real wave function, R2, and psi NLM complex conjugate R1. Now there it does do something because the higher spherical harmonics are not all real. Okay, and then I need to write my perturbation Hamiltonian here. Okay, and again, in general, it's a very complicated integral. This is known as the exchange or indirect integral, just because it comes from the cross terms. So if you want to work hard, you can go ahead and compute this thing for different NLMs. Here's the important thing for us. This thing is, even though it's not obvious, this turns out to be positive. And it turns out to be less than I in all cases. That's going to be a crucial thing for us. Because now if we look at this formula, we see that whatever J does, the minus sign is going to give the lower state because we're subtracting something positive from I. Okay, so the minus was the spin 1. And so this is telling us that the spin 1 state is always lower in energy than the spin 0 state. It's coming about from the fact that the exchange integral is positive. All right, so now let us go ahead and think about what the energy levels look like. So I'm going to do a graph of the energy levels. And we're going to label these states in spectroscopic notation. And so what that means is there's this code where you write 2s plus 1 as a pre-superscript, and you write L for the orbital angular momentum and J for the total angular momentum. In our case, 2s plus 1, s is always 0 or 1, so this is always going to be 0. This is always going to be 1 or 3. Okay, and so let's just see what we get. So I'm going to actually want a lot of space here. So I'm going to put, I'm going to leave about half a page of space. So if you happen to be taking notes, you'll probably want to do the same thing. And so way down here, I'm going to write my energy level for the ground state. So in terms of the individual wave functions, this was 1s, 1s. We put both of our electrons in the 1s state. And we gave them spin 0 because we had no choice. And they both have orbital angular momentum 0. Those are the s's. So L equals 0. Okay, and the only way to combine those into J is 0 plus 0 is 0. So the spectroscopic notation for this will be 1s0. This is the ground state. And this is what we've done before twice. And this is at negative 79.01 electron volts, which we got within 1% or 2 of. That's the ground state, and it's a para state, perihelium. Okay, now at the upper extreme, way up here at the top, I'm going to draw a dashed line. What does that represent? That's going to represent basically the highest energy I can have for a helium atom, because if I go higher than that, the idea is if I put in enough energy into the atom, I'll be able to take the electron and eject it completely and ionize it, and then it won't be helium anymore. It'll be a helium plus ion. So this level is the helium plus ion level, where one electron is completely removed. Okay, and the other is in a 1s state. And so its energy is minus z squared e squared over 2a naught, which turns out to be minus 54.4 electron volts. Okay, so all the states we're going to be talking about are in between there. And so now let's talk about the first state above the ground state. So what's that going to be? That's going to be a 1s 2s state. So I'm putting one electron in the 1s state, the other in the 2s state, which is NLM equals 200. Okay, and what we learned is that the s equals 1, or ortho, is lower in energy because of the exchange integral. And the spectroscopic notation for this is again 1s0, because the spin 0, there's no orbital angular momentum, and so J is again 0. This one's going to have spin 1, so it's 3. Again, it's S because there's no orbital angular momentum. And now J has to be 1, because if you add spin 1 to orbital angular momentum 0, you have to get 1. And this is at about, it turns out, minus 59 electron volts. So it's not to scale. This thing should be higher, but I'm trying to leave room for what goes above it. One thing that goes above it is I can put one electron in the 1s state and the other in the 2p state. So that's going to have slightly higher energy. But again, for that level, the s equals 0 para is higher than the s equals 1 ortho. So this is going to be a 1p, because now I have orbital angular momentum 1, and J is 1, and this is going to be 3p. And when I add spin 1 to orbital angular momentum 1 from here, that can be total angular momentum 0, 1, or 2. But they're roughly degenerate. In fact, they are degenerate without putting into account the fine structure. Okay, and so then I can repeat. I can go up here to the 1s, 3s, Okay, and again, I have an S equals 0. I have an S equals 1. Top one is para, the bottom one is ortho. And then I can have, so this is 1s0 again. This is 3s1. Notice in each column, everything's the same, except that in the ground state, there's no 3s1. Okay, and that's only because these are the same state. All right, and then for here, there's 1s3p. Again, it splits into a para and an ortho. This one is again 1p1. For angular momentum purposes, it's the same thing as the thing below it. But now there's a 3D state, because when n equals 3, then the angular momentum, orbital angular momentum can be 2. And so it does something like that. And this is 1d2 and 3d1, 2, or 3. This is again the para and the ortho. And then you can keep doing that. You can do, so not shown. Are the, for example, 1s, 4s, 1s, 4p, 1s, 4d, and now I can have 1s, 4f.
Professor?
Okay. Sorry, go
Professor?
ahead.
I'm sorry, was that supposed to be S equals 1 where you have 3D, 1, 2, 3?
You're talking up here?
Yeah.
Sorry, what's the question?
Is the bottom one supposed to be S equals 1?
Oh, yeah, sorry. Oh, no, wait. Yeah. Very good. That's S equals 1. Sorry, I'm going through this too quickly. Let's see, is everything else okay here? I think so. Okay, so up above here, I won't draw them, but there are a bunch of other pairs of lines. And we're getting closer and closer to this ionization level. Okay, and so you could have, for example, 1s, 5s, etc. Okay, and they just get closer and closer in energy to that ionization level. So you notice I've put 1s's for the first one in all cases, and so it's fair to ask, what about things like maybe 2s, 2s, etc. So why didn't I draw those? To answer that question, let's do a naive estimate of the energy of those. That's going to be minus z squared. This is before including the perturbation. So now if they're both in an n equals 2 state, I should divide by 1 over n squared, which is 1/4. They're both in the n equals 2 state. And then I just do the arithmetic for that. So this is minus 4 times 1/2 times 13.6 electron volts, which is about negative 27.2 electron volts. So that would be roughly the energy of that state. And now let's go back up here to our map. And we notice, aha, that energy would be above this energy. So that means if we try to put that much energy into this poor atom, what it's going to do is not go into this state. Instead, one of the electrons is just going to take off and leave. And so it will just become ionized, and that state won't exist. Okay, so this is not a state. This is above the helium plus ion line, and so it doesn't exist. And so if you think about it, anything where you put both of the electrons above the 1s level will not exist for the same reason. They'll all have too much energy, and that energy would just go into removing one of the electrons completely, and so you won't see it. Okay. So other things we can mention is all of this was in excluding fine structure, and I started off today by telling you that fine structure was important. And so more important for larger atoms. And so the fine structure is going to split the levels with different J. Okay, and so the ortho states in particular, for example, if I have a 3p012, those are different J values. This is a state with S equals 1. And now it's just going to split into 3 states like that. Same thing for my D states. They'll split into 3. Okay, then there's the hyperfine, and we'll be able to dispose of this very quickly. So the hyperfine, remember, comes about from the nucleus, but a 4-helium nucleus, meaning it's made out of a proton and a proton and a neutron and a neutron, has no spin. And if it has no spin, that means it has no magnetic moment, no magnetic dipole moment, because magnetic dipoles point in some direction, and any state that has no spin has no special direction for it to point in, so it has no magnetic dipole moment. It also has no electric quadrupole moment either, which it has in common with the hydrogen atom. Okay, and so there's no hyperfine splitting for helium. Except that some helium nuclei are not made out of proton, proton, neutron, neutron, but instead are 3 helium nuclei, which are made out of proton, proton, and neutron. And that has spin 1/2. And so then there's a small hyperfine splitting for that. So I'm just mentioning it so that you're aware that some helium has hyperfine and some, but most helium atoms do not because of the different nuclei that they have. All right, that's it for today. Sorry I went a little bit over, but that was a convenient stopping point. And so I'll remind you that on Monday, we have our first exam. So I'll see all your bright smiling faces in Davis Hall for the midterm. And I'll be happy to answer any questions you have.
So yeah, I have a few questions. Professor, so chapter 13, that's not in the midterm, is it? Is it
Chapter 13, yeah, so we're in the midterm, we're not going to be covering identical particles. That you can expect to see on your next midterm. So yeah, the first midterm, I'm going to be concentrating on perturbation theory and the variational principle and applications to that. So for example, we've applied these to the hydrogen atom. And so to the extent that we've applied it to the hydrogen atom, you should be familiar with how those applications work. But there will be nothing about, and I guess we did apply it to the helium atom, but there won't be anything intrinsically about identical particles on the exam.
I have another question. This last part here, could you explain that again? So it's hyperfine. You're saying if we don't have a spin, I'm sorry, I'm just slow. I'm just terribly slow. So if we don't have a spin, we don't have a magnetic moment, and there's no hyperfine splitting.
Right.
So yeah, let me get this all straight. This hyperfine went back to the electromagnetic interaction.
So the hyperfine is sort of by definition the thing that arises from the nuclear spin and or the nuclear quadrupole moment. Now the proton doesn't have any quadrupole moment. So when we did the hydrogen atom, we ignored that. For other atoms, you have to take it into account. But so for the hydrogen atom, it was just the fact that the proton has a magnetic dipole moment. That's what gave rise to hyperfine splitting. But for helium, there is no magnetic dipole moment. And so there's no hyperfine splitting for this isotope of helium.
So the hydrogen doesn't have a nucleus. It only doesn't have any nucleus. What do you call it? It only has a proton in its nucleus. Is that what you're saying?
That's correct. The nucleus of a hydrogen atom is just a proton.
So, and then you're saying in helium, there's like neutrons involved. That's why we have quadrupole.
So it has no quadrupole moment either.
Okay.
But it could. In general, a nucleus can have an electric quadrupole moment.
Can
so
or cannot?
when you're doing the hyperfine for some more complicated nucleus, you have to take into account that quadrupole moment.
Okay.
Okay.
So what does that do? That splits it into four? Is that what it does?
It splits it into multiple states depending on the other quantum numbers.
So that one where you split that p into three, what do you call that?
This
Is that a special moment in like that previous line?
This is the fine structure splitting. And I'm just drawing pictures of it. We're not calculating it, but I'm just saying that the fine structure splits these ortho states like this, because the fine structure gives a contribution that depends on J.
The hyperfine. I don't know. I feel like I'm struggling with some of these concepts. I've been struggling on chapter 12 in general. Like I had a hard time when I was reading it too. I still have a lot of questions in it.